Professor Belfrost's computer science class is back!
Hi, welcome back. And here's Professor Belfrost's class on computer science. And today we are going to explore another concept on computer science, continue our last lesson. And if we are already ready for today's episode, then let's go. Okay, so in the last episode, we have done with explaining things about a basic cache. And today we'll discuss more about the advanced things about cache memory. The first thing that we'll discuss is the replacement algorithms. Yeah. So it's actually replacement algorithms and why we need it. So we only need it for the associative and set associative techniques. Okay. And this algorithm must be implemented in hardware. So actually there are many kind of algorithm or the replacement algorithm that has been tried. The most effective one is least recently used that will replace that block in the set that has been in the case longest with no reference to it. How to use it? That we include a use bit for each line. Okay, that's the first replacement algorithm. The second one is that we use a first in, first out. Okay, it means that we replace the block in the set that has been in the cache longest time. Okay, and it's very easy to implement by using round robin or circle buffer techniques. The third technique is least frequently used, which means that we replace the block in the set that has experienced the fewest prefix. Okay, and actually, uh, we have shown, it has been shown that random replacement profiles only slightly inferior performance to an algorithm based on the usage. The next thing that we will going to discuss is write policy. So what is about write policy? So when a block that is proceeding to a case to be replaced, then there are two cases to consider. That if the old block in the case hasn't been altered, then it may be overwritten with new block without first writing out the old block. And if at least one write operation has been performed on a word in the line of a case, then the memory has to be updated by writing the line of the case out of the block memory before bringing the new block. Okay, there are two problems to um, to do with the write policy. The first is that more than one device may have access to main memory. So, if a word has been altered only in the case, then the corresponding memory will be invalid. And further, if the IO device is altered main memory, then the case word is invalid. The second problem, which is more complex, occurs when multiple processors are attached to the same bus and each processor has its own local case. And thus, if a word is altered in one case, then it could consequently invalidate a word in the other case. There are some techniques, and the simplest one is strike through. That we use this technique, that all write operations are made to main memory as well as to the cache to ensure that main memory is always valid. But it has disadvantage that it always generates substantial memory traffic and may create a bottleneck. There's a second technique that is introduced here is known as write back. So for write back, it minimizes the memory, minimize the memory writes, and with write back, then updates are made only in the cache, and when an update occurs, the bit or use bit associated with the line is set. Okay, and yeah, even if a write policy is used, then the other case may contain valid data, and there are some way to maintain this case coherency. Let's see. The first one is to bus watching with write through. That we have each case controller to monitor the address line to detect an operation to the memory by other bus masters. The second one is hardware transferation that use additional hardware to ensure that all updates to memory via cache are reflected in all cache. The third one is by non-cacheable memory. The under pressure of memory is shared by more than one processor, and that is designated as a non-cacheable cacheable. Okay. Then next topic is line size. So another design element that we need to consider is the line size. So when a block of data is retrieved and placed in a cache, not only the desired word but also some number of adjacent words are retrieved. And as the block size increases from very small to larger size, the hit ratio will at first increase because of the principle of the locality. What is the principle of locality? It states that data in the vicinity of reference word are likely to be replaced in the near future. As the block size increases, the more useful data are brought into the cache, and the hit ratio will begin to decrease. However, as the block becomes even bigger, the probability of using the newly fetched information becomes less, then the probability of reusing the information that has to be replaced. Now, there are two specific effects that come to play here. First is that larger blocks reduce the number of blocks that fit into a cache. And second is that as a block becomes larger, then each additional word is farther from the requested word and therefore less likely to be needed in the near future. Then we'll discuss about number of cache. Okay, so when cache first be introduced in typical system had only a single cache, but more recently that we have been introduced with multiple cache. Okay, then let's see the design issue concern the number of levels of cache and the use of unified versus split cache. First, we are going to discuss multi-level cache. So as logic density has increased, it has been possible to have a cache on the same chip as the processor, the on-chip cache. Okay, so the on-chip cache reduce the processor external bus activity and therefore speed up the execution time and also increase the overall system performance. Okay, because of the short data path internal to the processor compared to the bus length. Okay, so it is possible to have a zero-weight state bus cycle. Also, during this period, the bus is free to support other transfers. And the inclusion of an on-chip case leaves open the question of whether an off-chip or external case is still desirable. The answer is actually yes, and most contemporary design include both on-chip and external cache. The simplest such organization is known as a two-level cache. Okay? Maybe you've seen the figure before. Here we have something called L1, which is fast, and L2, this is a little slower. Okay, there's a reason for this. Okay, so if there is no L2 cache and the person makes an access request for memory location in the L1 cache, then the person must access DRAM and ROM memory across the bus, and this is slow, and this will result in poor performance. So L2 is an SRAM. Okay, then frequently the missing information can be quickly retrieved. That's the reason. And there are two features of this contemporary cache design. First, for an off-chip L2 cache, the many design do not use the system bus as the path for transfer between the L2 cache and the processor, but use a separate data path so as to reduce the burden on the system bus. And the second one is that with the continuous shrinkage of the processor components, that a number of processors now incorporate the L2 cache on the processor chip, improving the performance. Okay. So with the increasing availability of an on-chip array available for cache, then most contemporary microprocessors have moved the L2 cache onto the processor chip and also added the L3 cache. And originally, the L3 cache was accessible over the external bus, but nowadays also it has been incorporated on chip L3 cache. Now we discuss about unified versus split cache. So more recently, it's become common to split a cache into two, so one dedicated to instruction and the other dedicated to the data. So these two cache both exist at the same level, typically as 2L1 cache, okay, the fastest one. So when the processors attempt to fetch an instruction from memory, it first consult with the instruction L1 cache. Then, when the processor attempts to fetch data from memory, it first consult the data L1 cache. And there are two potential advantages of a unified cache. So for a given cache size, then unified cache is a higher hit rate, okay, than the split cache because it's balanced the load between the instruction and data fetch automatically. Okay. A second one is that only one cache needs to be designed and implemented. But actually, the trend says something different. Trend is towards split cache or unified cache, particularly for a superscalar machine. Okay. which emphasize the parallel instruction execution and preparation of predictable future instruction. So maybe you ask why? Because there is a key advantage of a split case design. That is, it eliminates contention for the case between the instruction parasitic code unit and the execution unit. And this is important in any design that relies on the pipelining of instruction. Okay, so yeah, suppose that now we have a unified instruction data case. Then when the execution unit performs a memory access to learn store data, then the request is submitted to the unified case. And if at the same time, this is the key here, if at the same time the instruction prefetcher is used to write request to the cache for an instruction, then the request will be temporarily blocked. So the case can replace the execution unit first, enabling it to complete the currently executing instruction. And this can degrade the performance by interfering with the efficient use of the instruction pipeline. So the split case structure is said to have overcome this difficulty. Okay, I will skip for a specific architecture. And let's see if we have. Okay, this is quite important. So performance characteristic of two-level memories. So yeah, reference is made to a case that acts as buffers between memory and processor, creating a two-level internal memory. Okay, and there is a property that is known as locality to provide improved performance of a comparable one-level memory. So let's see what is locality. So the basis for the performance advantage of the two-level memory is a principle known as locality of reference, and states that memory reference tend to cluster. And over a long period of time, the cluster in use change, but over a short period of time, the processor is primarily working with fixed cluster of memory reference. Okay? So there are two reasonings that we make use of principle of locality. First one is that except for branch and construction that constitutes only a small fraction of all program instruction, then program execution is sequential. Therefore, in most cases, the next instruction to be fetched immediately follows the last instruction first. And the second reason is that it is very rare to have a long uninterrupted sequence of process calls followed by the corresponding sequence of programs. Rather than a program remains confined to a rather narrow window towards the invocation. The third reason is that most iterative construct consists of a relatively small number of instructions repeated many times. The code is therefore confined to a small contiguous portion of the program. And the fourth one, the last one, that in many programs, much of the computation involves processing data structures such as arrays, sequence of records, and in many cases, that the successive reference to this data structure will be considered located data items. Okay, so a distinction is made in this book that I use between spatial locality and temporal locality. So there are two types of locality. The first one, which is spatial, refers to the tendency of execution to involve a number of memory locations that are clustered, and this reflects the tendency of a processor to access instruction sequentially. Whereas with temporal locality, it refers to the tendency for a process to access memory locations that have been used recently. Okay, so traditionally, temporal locality is exploited by keeping recently used instruction and data values in a cache memory and by exploiting a cache hierarchy. And spatial locality, on the other hand, is generally exploited by using larger cache block and incorporating prefetching mechanisms into the cache control logic. Before the formula, I will just skip it because we're not going to this discussion. Yeah, we have done with cache memory, and we will go to internal memory. Okay, so actually for memory, I plan to have 6 or 7 videos on it. So yeah, this is the second video on memory, right? This is we will discuss a little about internal memory this video and will continue on the next video. Okay, so let's see. So there are two basic forms of semiconductor RAM. They are dynamic RAM and static RAM. And SRAM is it's clearly faster. I will show you the reason. But it's more expensive and less dense than DRAM. Okay, DRAM, for the same reason too, because it's uh, cheaper, used in most of the main memory. Also, error correction technique are common used in memory. Simple. It involves adding redundant bits. Okay, we may call it parity. That function of the data bits to form an error correcting group. Then to compensate for the relatively slow speed of the DRAM, a number of advanced DRAM organizations have been introduced. Some of them are synchronous DRAM and RAM bus DRAM. We'll see later. Okay, we'll discuss 5.1 first for this video. Okay, so semiconductor main memory. Okay, so in early computers, that the most common form of random access storage for clear memory imply an era of donut-shaped magnetic loops that referred to as cores, and hence the main memory is often referred to as core, a term that persists to this day. Okay, and today maybe we just see that kind of technology not commonly used again, and we have moved to semiconductor technology. Okay, so the basic element of semiconductor memory is a memory cell, and all semiconductor memory cells share certain properties, though there are a variety of electronic technologies that are used. First one, they exhibit two stable or semi-stable states, which can be used to represent by the 1 and 0. The second is that they are capable of being written into at least one set state, and they are capable of being read to sense the state. And here is the picture of memory cell operation. The figure on the left will show you how to do write, and the figure on the right show you how to do the operation of RAM. Okay, so we have the select terminal to select a memory cell for read or write operation, and the control terminal indicates read or write. And for writing, the other terminal provides an electric signal that sets the state of the cell to 1 or 0. For reading, that terminal is used for output of the cell state. Okay. Now we'll see a little about DRAM and SRAM. So here's the summary, the table of semiconductor memory type. So we have RAM, we have ROM, we have PROM, EPROM, EEPROM, and flash memory. Only RAM, which is volatile, and the other are non-volatile. Why is volatile? Why is it not volatile? Maybe you have known it before. Volatile means that it will, I mean that it is, yeah. You see, this is electrically, this is mass electrically. I also will discuss it when I go through this explanation. Okay. So the most common semiconductor technology that maybe you have used is you have known so far is RAM, and yeah, actually, it is something that the terminology is not really correct. Okay, because actually all of these type in the table is random access. But one distinguishable characteristic of RAM is that it is possible both to read data from the memory and to write the data into the memory easily and rapidly. Okay, so it is not very correct use random access, because actually all of them are random access. And also the other distinguishing characteristic of RAM is that volatile. Volatile means that it must always be provided with constant power supply, or if the power is interrupted, then the data are lost. This is the meaning of volatile. So RAM can only be used as temporary storage. And there are two types of RAM that is used in computers. This is DRAM and SRAM. DRAM, dynamic RAM, is the technology used by making the cells that store data as charged on capacitor. Okay, and the presence or absence of charge in the capacitor is interpreted as a binary 1 or 0. And because capacitors have a natural tendency to discharge, then the dynamic RAMs require periodic charge refreshing to maintain the data storage. And thermodynamics actually comes to this tendency of the stored charge to leak away, even with power continuously applied. So here's the figure that shows you the typical DRAM structure of an individual cell that stores 1 bit. So you see here we have transistor, we also have storage capacitor. Okay, and it's connected to the address line, you see, and also have a bit line B. Okay, so yeah, the transistor here acts as a switch that's closed if a voltage is applied to the address line, and open if no voltage is present on the address line. Okay, so there are two things that can be done: for operation and read operation. I leave it for you to read it by yourself. Although the DRAM cell is used to store a single bit, it actually is an analog device because a capacitor can store any charge value within a range. The threshold value determines whether the charge is interpreted as 1 or 0. There we have static RAM. Okay, we'll discuss till SRAM versus DRAM for this video. Okay, I'll cut till there. So in contrast with SRAM, it is a digital device that uses the same logic element used in the processor. And in SRAM, the binary value are stored using traditional flip-flop logic gate configuration. Okay, flip-flop has been discussed before. That's why I place that discussion first before I give you the explanation under internal memory. Okay, so static RAM will hold its data as fast as the power is supplied to it. Okay. As in the DRAM, the SRAM address line is used to open or close the switch because it controls through capacitor. Okay, so this is for SRAM. You see, there are many transistors: 1, 2, 3, 4, 5, 6. Okay, and there are two bit line. Okay, not only one. Okay, we have bit line B and bit line complement B. Okay, that is the difference. Okay, so when a signal is applied for the line and two places are switched on, allowing a read or write operation. Okay, and you can see the explanation. So what is the difference between SRAM and DRAM? That both static and dynamic RAM is actually volatile. That is, power must be continuously supplied to the memory to preserve the bit value. But a dynamic memory cell is simpler and smaller than SRAM. Thus, the DRAM is more dense and less expensive than the corresponding SRAM. But on the other hand, the DRAM requires that the supporting refresh security. And for larger memories, then the fixed cost of the refresh security is more than compensated for by the small variable cost of DRAM. And thus, the DRAM tends to be preferred for large memory requirements. And the other point is that the SRAMs are generally somewhat faster than DRAMs, and because of this related capacity, the SRAM is used for the cache memory, both on and off chip, and DRAM is for the main memory. So it's also related to the usage. Okay, maybe that's for today. Here's a little quote before I end this video. So you're never too old to set another goal or to dream a new dream. That's by C.S. Lewis. And that's all our lesson for today. Thanks for watching. And here's your to-do list. So please subscribe, give a like, comment, and share this video to your friend. I'll be back on every Monday on the same class in computer science. And don't forget to visit our website at https://science.xyz.unaux.com. Keep watching and be thoughtful. Goodbye. See you on the next episode.